In question 7, you're given this diagram here. You're told that it represents the plan supports of the roof of a building, and all these triangles are scalene, and they're all of different sizes as well. In part A of this question, you're asked to explain what's meant by a scalene triangle, and this is just something you would have learned in primary school really, that a scalene triangle has 3 sides of unequal length and 3 interior angles of unequal measure. Next, you're given a little bit of information about the diagram. You're told that this triangle EFG here is the image of the triangle CDE, that's this one, under enlargement, and that this one is also the same as this triangle under enlargement. So what that means is the triangles are all similar in that their internal angles are all the same. And you're given just a couple of lengths. You're so told that this length here is 7.2, this length BC is 8, the length CD is 9, and this angle here, DCB, is 60 degrees. When you're given a diagram like this, I find it easiest to try and put down as much information as you can before even getting started on the questions. So the kind of things you can work out immediately are a few angles. For example, immediately I can say that this angle here is 60 degrees, because if this angle here is equal to this angle and this angle is equal to this angle, which is going to be the case because those triangles are similar, then all of those 3 angles there have to add to 180 degrees, all those angles have to add to 180 degrees, and you can just work out then that this angle is 60 degrees because this angle is 60 degrees. Similarly, you know that these 3 internal angles here add up to 180 degrees, and because these 3 triangles are similar, we know this angle here is equal to this angle, and because this is a straight line, we know all 3 of these angles add up to 180 degrees. So we have, in one case we have a dot, a circle, and 60 degrees add to 180, and in this case we have a dot, a circle, and some angle we don't know yet add to 180, but because of those 2 relationships we can say that this angle is 60 degrees. And we can also say then, because these 3 triangles are similar, that this angle is also 60 degrees, and this angle is 60 degrees as well. The first thing you have to work out then is this length here, FG. Now, this is going to take a few steps, and it takes picking something very specific out of the information you're given. That you're told the enlargement between this triangle EFG and CDE is the same as the enlargement between CDE and ABC. Without that little bit of information, you won't actually be able to solve this question, at least not as far as I can tell. Because we have that bit of information that the enlargements are the same, then we can compare lengths from all 3 triangles together. So for example, we take this length EF divided by the length CD. That's equal to the same ratio as the ratio between CD and AB, and that's what this statement here is. And remember, that's only true because the enlargements are the same between adjacent triangles. So that tells me that this length EF is 11.25 meters. And the only reason I'm doing that first is because the left side of this triangle is the only side that I have more than 1 bit of information about, because I have 2 lengths on the left. So I have to find 2 lengths on the right so I can start comparing the length on the right, which I'm looking for this FG. I could also have found this length ED by the same kind of ratio. Now that I know this length 11.25, then I can compare this triangle with any other triangle. So I'm going to take this length FG and compare it to the right side of this triangle, 8, and compare the 11.25 that I just found with this side here, 7.2, and that gets me the FG is 12.5 meters long. Next I have to find this length here, BD, This part is a little bit more straightforward because we're looking at just a single triangle, and we have side lengths and we have one angle. So the way you're going to do this one is with the cosine rule. Using the cosine rule, we can say that this length BD that we're looking for squared is equal to the sum of the square of the other two sides minus twice the product of those two side lengths times cos of the angle opposite to the one we're looking for. So we get BD squared is equal to 8 squared plus 9 squared minus 2 times 8 times 9 times cos of 60. And you work that all the way through and you get 8.544 meters. In part D, you're told that the center of the enlargement is O, and you have to find the distance from O to the point B. So what they mean by the center of the enlargement is the point where if you take this line here and extend it in this direction, take this line and extend it in that direction, where they meet is going to be some central point that the triangles are expanding away from, and you have to find the distance from that point to this point B. There's possibly some coordinate geometry techniques that would work here, but just in terms of pure trigonometry, we can construct a new triangle and try and work it out that way. If we can find as many lengths and as many angles as possible, we'll be able to get that length. The first thing I want to do is to try and find a few more angles, and to do that I'm going to take a triangle that I have the most information about and then try and get all the rest of the information about it. So I'm going to find first of all this length here, AC, and you do that using the cosine rule because again I have a side length that I don't know, I have two side lengths that I do know, and I know the angle that's opposite the side length I'm looking for, so that warrants the cosine rule. And with that I guess that this length AC here is 7.632 meters. With that information then I'm going to try and find one of the angles, in particular this one here, ACB. So using the sine rule I can figure out that sine of this angle divided by this length is equal to the sine of this angle divided by this length. And using that I can find out that this angle here is about 55 degrees. Of course, when you undo this sine operation, when you take the inverse sine of 0.817, you should get two angles because sine of an angle is going to be 0.817 at two different angles. So this angle here could be 55 degrees or it could be 125 degrees. But we can rule out the 125 degrees because we know if this was 125 degrees, then this angle plus this angle is 185, which is more than the maximum angle that you can have in a triangle because all the angles have to add up to 180 degrees. So we can rule out the 125 degrees and that just leaves us with 55. Now I have my first bit of really concrete information about this new triangle OAB that I'm trying to form. Because I know that these two angles here, 60 and 55, I know I can add them up and that will tell me this angle here, 115 degrees. That's just one of the theorems that the two internal angles will add up to the opposite external angle. I also have this length here, AB, so one more piece of information hopefully and I'll be able to work out anything I want about this triangle, including this length OB that I'm looking for. In order to get my next bit of information, I'm going to have to take a bit of a roundabout route to find this angle here, the one I've marked with the circle. I know that sine of this angle divided by 8 is equal to sine of this angle divided by this length here, which is 8.544 that you worked out in part B, or was it part C? Anyway, using that I can just use the sine rule to get this angle 54 degrees, which again I'm going to get two angles. The other one is going to be 126 degrees, but again I know that the internal angles of a triangle have to add up to 180 degrees. So if this is 126 degrees, then this angle couldn't be 60 degrees, but we know this is 60 degrees, therefore this angle has to be 54 degrees. just a very quick definition of corresponding angles, and I can tell that this angle here is also 54 degrees. So now if I go back to my triangle here, I now have this side length AB, I have 115 degrees, and I have this angle is 54 degrees. So with that, I should be able to find out another good bit of information, and then I'll be able to find the length OB that I'm looking for. Here we go then into the home stretch, as it were. The angle AOB, that's the angle at this origin point O, is going to be 11 degrees, because I know that the other two angles are 115 and 54, and they have to add up to 180. With that information then, I can find OB by using the sine rule again. So the length divided by the sine of the opposite angle is equal to one of the other lengths divided by the sine of the opposite angle. And that gets me that OB is 34.2 meters. In the very last part of this question, you have to find out whether this plan meets a certain condition, that this height, this point here, G, can't be higher than 11.6 meters off the horizontal line BF. That's this bottom one. So how are you going to figure that out? Well, we can work out what this angle here is, and we know what this length is, so hopefully you should be able to figure it out based on that. So first of all, to figure out what this angle here is, I know that all three of these angles add up to 180 degrees. I know this angle is 60 degrees. I know that this angle is 54 degrees. We worked that out in the last part of the question. So I can then work out what this angle is using this. I know GFH, that's the angle I'm looking for here. That's this one. That's equal to 180 minus one of the other angles minus the other angle. So I get 180 minus 60 minus 54, which is 66 degrees. So I know that this angle here now is 66 degrees. Here is my new triangle then. I have F and G are already given. I'm making this point H, which is where this vertical line touches the line, the extension of the line BF. So I've worked out this angle is 66 degrees. In one of the early parts of the questions, I think it was part B, we worked out that this length here is 12.5 meters. So now I have a right angle triangle, and I know it's right angled because this line here we're told is horizontal, and I'm looking for the height above that, which is so it's going to be vertical, and the angle between horizontal and vertical is 90 degrees. To finish that off, I know I have a right angle triangle now, so I can just use the basic trigonometric identities for that. I can say that sine of this angle is equal to this vertical length that I'm looking for divided by the length of the hypotenuse, which is 12.5 meters, and that gets me that this length here, GH, is 11.4 meters. And don't forget, the question is, does the plan meet this condition that that height is less than 11.6 meters, or less than or equal to 11.6 meters even, which is true here because 11.4 is of course less than 11.6, therefore the plan meets the condition. And really don't forget to include this qualifying factor here, and then the statement at the end that you're actually answering the question they're asking. I mean, you will get most of the marks for having the calculation, for knowing what you're doing, but you really do still have to finalize it.